Welcome back to the deep dive. We take these huge, sometimes really overwhelming curricula and research papers and try to boil them down into something practical, an audio-on-demand guidebook, basically.
Yeah, exactly.
And today, our mission is really for those of you aiming for, well, true technical mastery in deep learning. We're synthesizing the absolute foundations. Think of this as the guide you'd want if you were aiming to become an AI pioneer, or maybe even, a teaching assistant helping others navigate this stuff.
That's a great way to put it.
Yeah.
We're essentially taking, what is it, a 60-hour, 5-unit course?
Yeah, something like that.
And packaging it into something focused, intuitive. This isn't just passive listening. The idea is you really internalize the why.
Yeah.
The why behind every concept, from the basic algorithms right through to deployment tools.
Right.
We want to use analogies, a dartboard, the rolling ball, stuff like that, make it stick, and connect everything to, well, the real world, Netflix, Google, Tesla, how they actually use this.
That wow factor.
Exactly. So the skills you build are solid,
Yeah.
Relevant for the next 10, 15 years. It's about that long-term foundation.
I like that focus, the resilience aspect. So we're going from the kind of philosophical underpinnings of AI all the way to the practical tools you need. Let's start where any good course does. Unit 1, getting the language right, the basic ways machines learn. Okay, first hurdle, defining the key terms. AI, ML, deep learning. People throw these around, sometimes interchangeably, but we need clarity.
Yeah, absolutely. It gets muddy fast.
I find the nested circles analogy helps, or maybe Russian dolls. The biggest concept, the outermost circle, is artificial intelligence.
Right.
That's the grand ambition, right? Any technique that lets computers mimic human intelligence. Could be a simple chess program, could be, a complex recommendation engine. It's broad.
Very broad. Then, moving inside that big AI circle, you've got machine learning, ML.
Right.
And ML is specifically the subset where systems get better at a task through experience, through data, without being explicitly programmed for every single rule.
That's the key bit, right? Learning from data. You don't code every possibility.
Exactly. The system infers the rules itself. You feed it data, it learns.
The classic example, and I think the curriculum hits this hard, is the spam filter in your email.
Perfect example.
You never told it if an email has these exact 50 words, it's spam. No way. It just learned the patterns from millions of emails people marked as spam or not spam. It learned by seeing examples.
Right. It generalized from the data. Now, at the very core, the innermost circle, that's deep learning, DL.
Okay, the main event.
And here's the thing people often miss. DL is simply a subset of ML. It uses specific kinds of algorithms, artificial neural networks, that have multiple hidden layers. Many layers.
So that answers the why deep question. It's not about it being profoundly difficult conceptually.
Not necessarily, no.
It's literally about the depth of the network, the number of layers.
Precisely. It's an architectural description. More layers, deeper network.
Okay, but what's the big deal about having multiple layers? What makes that so powerful compared to, say, shallower ML?
Great question. The depth is what allows for automatic feature engineering or feature hierarchies. See, in traditional ML, say for images, you might have to figure out how to tell the model to detect edges or corners or textures.
Right, you'd craft those features yourself.
Exactly. With deep learning, the network learns these features itself, layer by layer. The first hidden layer might learn to spot simple things, like horizontal or vertical lines.
Okay.
The next layer might combine those lines to detect basic shapes, circles, squares. Then the layer after that might combine shapes to recognize more complex parts, like an eye or a nose or a car wheel.
So it builds up complexity automatically.
Yeah. Yes. This progressive hierarchical feature learning is what makes deep learning so powerful for complex data like images or sound. It figures out the important representations on its own. Getting that is really fundamental.
Got it. Okay, so we have the structure defined. Now, how do these machines actually learn? The curriculum highlights 2 fundamental modes, supervised and unsupervised learning.
Right, and pretty much every project you encounter will fall into one of these 2 buckets, or maybe a combination. Supervised learning is basically learning with a teacher.
Meaning the data has answers attached.
Exactly. The training data is labeled. For each input example, you also provide the correct output, the ground truth. The model makes a prediction, compares it to the true label, calculates the error, and adjusts itself to get closer next time. It's constantly being corrected.
Makes sense. And the applications seem really wide because, well, often you can get labels even if it's sometimes expensive or time-consuming.
Definitely. Think about classification tasks like medical imaging, input, an X-ray label, dot pneumonia, or healthy.
Or predicting house prices. That's regression, right?
Input, house features, square footage, number of bedrooms, location, label,
Yeah.
the actual known sales price. The machine learns the mapping from features to price based on those labeled examples.
Okay, so that's supervised. What about the other side? Unsupervised learning.
This is learning by exploration. No teacher, no labels, no right answers provided during training.
So, what's the goal then, if it doesn't know the right answer?
The goal is internal. It's about finding hidden structures, patterns, or relationships within the data itself. The algorithm is just looking for interesting structures.
Okay, examples help here. What's a classic unsupervised task?
Customer segmentation is the textbook one. Imagine a retailer feeds in tons of purchase history data. No labels like good customer or bad customer.
Right.
The unsupervised algorithm might automatically cluster customers into groups based on their buying habits. Maybe it finds a group of high-spending city dwellers and another of occasional suburban shoppers. The machine finds the groups. The human analyst interprets and names them later.
Ah, okay. It discovers the categories.
Precisely. Another huge one is anomaly detection. Think credit card fraud. You feed in millions of transactions. The system learns what normal transaction patterns look like. Then, when a transaction comes in that looks really different, really deviates from that norm, it flags it as potentially fraudulent. It spots the outlier without ever needing examples explicitly labeled fraud.
Got it. So knowing if your data has labels or not is the first big decision point. It dictates whether you go supervised or unsupervised.
Absolutely. That's a core piece of mastery right there. Recognizing the paradigm based on the data you have.
Okay, foundational concept number 3, and this one is so critical for actually fixing models when they go wrong. Bias and variance.
Oh yeah. If you're going to guide others or troubleshoot your own work, you have to have this down cold, get this right, and you immediately have clues about how to improve a model that's not performing well.
The curriculum uses the dartboard analogy, which I think is brilliant. Let's unpack that.
Love the dartboard analogy.
Okay,
so imagine you're throwing darts. The bullseye is the perfect prediction. The ideal model has low bias and low variance. Your darts are all tightly clustered right in the center. Perfect accuracy, perfect precision.
That's the dream. But reality is usually messier. Let's talk failures. First, high bias. What does that look like on the dartboard?
High bias means your throws are consistent. They all land close together. But they're consistently hitting the wrong spot.
Yeah.
Maybe they're all clustered tightly in the top left corner, far from the bullseye.
Okay, consistent but wrong. What does that mean for the model?
It means the model is underfitting. It's too simple. It hasn't learned the underlying patterns in the data properly. It's making systematic errors. Crucially, it's performing poorly, even on the training data it has already seen.
Ah, so if my training error itself is high, that's a big clue for bias.
Exactly. High training error screams high bias or underfitting. The fix: your model needs more power. Increase its capacity. Add more hidden layers. Add more neurons per layer. Maybe engineer better features if you're not using deep learning's automatic feature engineering. Make the model more complex.
Okay, that's high bias underfitting. What about the other side of the coin? High variance. What's the dartboard look like now?
High variance is the opposite problem. Your throws are all over the place, scattered wildly around the board. Maybe some hit the bullseye by chance, but there's no consistency, no precision. The grouping is terrible.
So, inconsistency. How does that relate to the model?
High variance means the model is overfitting. It's learned the training data too well. It hasn't just learned the signal. It's basically memorized the noise and random fluctuations specific to that training set.
Like memorizing the answers for a practice test,
Exactly.
but then failing the actual exam because you didn't learn the concepts.
Perfect analogy.
Yeah.
The model performs great on the training data, low training error, but when you show it new, unseen data, the test set, its performance tanks. The test error is high. It fails to generalize.
Okay, so the signature is low training error, high test error. That tells me I'm overfitting. What are the go-to solutions then, if I see that pattern?
Number one is usually regularization. Techniques like L1 or L2 regularization add a penalty to the loss function for large weights, discouraging the model from becoming too complex.
Okay,
But probably the most widely used, especially in deep learning, is dropout.
right, dropout. How does that work intuitively?
During training, for each training example, dropout randomly drops or ignores a certain fraction of neurons in a layer, like maybe 20% or 50% are just temporarily switched off.
Okay. Why does that help?
It forces the network to become more robust. No single neuron can rely too heavily on any other specific neuron. because that neuron might be dropped out at any moment. It encourages the network to learn redundant representations, different ways of capturing the same information. This makes it less sensitive to the specific quirks of the training data and improves generalization.
Clever. So regularization like dropout. What else?
Getting more data is almost always helpful against overfitting. More diverse examples make it harder for the model to just memorize noise. Sometimes reducing model complexity can help too, but often regularization is preferred first. Mastering this bias-variance trade-off, knowing whether to increase complexity or apply regularization, that's really the heart of Unit 1 troubleshooting.
Okay, that clarity on bias and variance, underfitting and overfitting is crucial. It sets us up perfectly to actually build the thing. Unit 2, the architecture, the artificial neural network, or ANN, the AI brain.
Right, so an ANN, as the name implies, is inspired by the biological neural networks in our brains. But, it's a very simplified mathematical abstraction. Don't push the brain analogy too far.
Good point. Keep it grounded.
In the most common type, the feed-forward network, information flows strictly in one direction, from input through the hidden layers to the output. No loops back, at least not in the basic structure.
Let's break down those parts. Input layer is pretty straightforward.
Yeah, that just takes your raw data, pixel values from an image, numerical features from a data set, word embeddings from text, whatever it is.
Then the hidden layers. This is where the real work happens.
Exactly. These are the layers between input and output. They perform the computations, the transformations. This is where the network learns those hierarchical features we talked about. More hidden layers generally means the network can learn more complex patterns. That's the deep learning.
And finally, the output layer.
Yep, that produces the final result. It might be a single neuron for a regression prediction, like a house price, or multiple neurons for classification, like one neuron per possible class, dog, cat, bird, perhaps with a softmax function to give probabilities.
Okay, but inside each neuron, in those hidden and output layers, there's a key component doing the decision-making, right? The activation function.
Absolutely critical. Without activation functions, the entire network, no matter how many layers deep, would just be doing a series of linear transformations. Basically one big matrix multiplication.
Which is limited.
Very limited. It could only learn linear relationships between inputs and outputs. Activation functions introduce nonlinearity. That's what allows the network to learn incredibly complex, wiggly decision boundaries needed for real-world problems.
What's the analogy here? The curriculum mentions a light switch.
Yeah, that's a decent starting point.
Yeah.
The activation function takes the weighted sum of all the inputs coming into the neuron and decides whether that signal is strong enough for the neuron to fire or activate and pass information onwards.
And the go-to activation function these days seems to be ReLU, Rectified Linear Unit.
Oh yeah, ReLU is king for most hidden layers. It's super simple computationally.
How does it work? The analogy I liked was a one-way valve for water.
That's a great one. If the input signal, the weighted sum, is positive, ReLU just lets it pass through unchanged. Output equals input.
Okay.
But if the input signal is 0 or negative, ReLU outputs 0. It clamps it off. Simple as that. Output equals 0 input.
And that simple nonlinear clamp is enough to give the network its power.
It's incredibly effective and computationally very cheap, which helps training speed. But for mastery, especially if you're guiding others, you need to know its potential downside.
There's always a catch. What's the issue with ReLU?
The dying ReLU problem. Imagine a neuron gets hit with a really large negative gradient during backpropagation. This could push its weights in such a way that the input it receives is consistently negative.
Okay.
If the input is always negative, ReLU always outputs 0. And if the output is 0, the gradient flowing back through that neuron during backpropagation is also 0.
So it stops learning.
Yeah, exactly. Its weights never get updated again. The neuron is effectively dead for the rest of training.
Yeah.
It contributes nothing. If too many neurons die, the network's capacity is severely reduced.
Okay, that's a crucial troubleshooting point. If your model suddenly stops improving, dead ReLUs could be a suspect. What's the fix?
The common fix is to use a variant, like leaky ReLU. Instead of outputting exactly 0 for negative inputs, leaky ReLU outputs a very small positive value, like 0.01 times the input.
So it leaks a tiny bit.
Precisely. That tiny slope means there's always some gradient, even for negative inputs. It prevents the neuron from dying completely and gives it a chance to recover later in training. There are other variants too, like pre-BLU or ELU, but leaky ReLU is a good first defense.
Got it. Okay, so we have the network structure, the neurons, the activation functions. Now, how does it actually learn? We need the engine. That brings us to backpropagation and gradient descent.
The absolute core of how neural networks learn. They work hand in hand. First, backpropagation.
This is about figuring out the error.
It's about figuring out who is responsible for the error. After the network makes a prediction, forward pass, you calculate the loss, how wrong it was. Backpropagation is the algorithm that efficiently calculates the gradient of that loss with respect to every single weight and bias in the network.
So it traces the error backwards.
Exactly. It uses the chain rule from calculus to distribute the error signal back through the layers from output to input. It tells each connection, okay, you contributed this much to the final mistake.
Like assigning blame, almost.
Kinda, yeah. It quantifies the contribution of each parameter to the overall error. It's like learning from mistakes in school, tracing back where you went wrong in your calculation.
Okay, so backprop tells us how much each weight needs to change. But how do we actually make that change effectively? That's gradient descent.
Precisely. Backpropagation gives us the direction of steepest descent for the error, the gradient. Gradient descent is the optimization algorithm that takes that gradient information and uses it to update the weights and biases to minimize the error.
The analogy here is rolling a ball down a hill.
The classic and still the best one. Imagine the loss function creates a landscape with hills and valleys. The height represents the error. We want to find the lowest point, the bottom of the deepest valley, minimum error.
And we're blindfolded.
Right. We can't see the whole landscape. We only know the slope right where we are. That's the gradient calculated by backpropagation. Gradient descent just says, take a small step downhill in the direction opposite to the gradient, the steepest descent.
And repeat.
And repeat, iteratively. Step by step, you roll the ball down the hill, hopefully settling in a nice low valley representing a good set of weights for your model.
This brings us to maybe the single most fiddled with knob in deep learning, the learning rate.
Oh, absolutely. The learning rate determines the size of the steps you take down that hill. It's a hyperparameter you have to set.
The curriculum suggests 0.001 as a common starting point, like a Goldilocks value.
Yeah, 1E3 or 0.001 is a very standard starting point for many optimizers like Adam. But choosing the right learning rate is crucial, and getting it wrong has very clear consequences. This is vital knowledge for anyone guiding others.
Okay, walk us through the risks. What if my learning rate is too high, my step size is too big?
If your steps are too big, you can literally leap right over the bottom of the valley. You might even jump up the other side. The loss doesn't decrease, it might oscillate wildly or even diverge, just explode towards infinity. Your model completely fails to train.
Okay, so exploding loss means learning rate might be too high. What about too low? Tiny steps.
Too small a learning rate, and your training will be incredibly slow. You're just crawling down the hill. It might take ages to reach the minimum. Worse, you might get stuck in a shallow dip, a local minimum, thinking you found the best solution when there's a much deeper valley nearby, but your steps are too small to get out of the rut.
So it's a trade-off. Finding that sweet spot is key.
Absolutely. And often you don't use a fixed learning rate. Techniques like learning rate schedules gradually decrease the learning rate during training, taking bigger steps initially, then smaller, more careful steps as you get closer to the minimum. Tuning this is often the first thing you try when optimizing a model.
Makes sense. Okay, we've built a general purpose brain and figured out how it learns, but standard ANNs, even deep ones, can struggle with certain data types. Images, for instance, they're huge.
Exactly. Feeding raw pixel values from, say, a 1,000 by 1,000 pixel image into a standard fully connected network. The number of parameters explodes. It becomes computationally infeasible and often doesn't work well because it ignores the spatial structure of the image. Pixels near each other are related.
So we need a specialized architecture. This brings us to Unit 3. Teaching machines to see with convolutional neural networks, CNNs.
Right. CNNs are the workhorses of computer vision. They are specifically designed to process grid-like data, especially images. They have specialized layers that exploit that spatial hierarchy.
The analogy is like having specialized filters for a camera, or maybe like our own visual cortex.
Both work well. Think about how you see. You don't process every raw photon individually. Your brain looks for edges, textures, shapes, objects. CNNs do something similar using convolution layers.
Okay, let's break down convolution. What's happening there?
Imagine you have a small grid of weights. It's your filter or kernel. This filter is designed to detect a very specific, simple feature, like a vertical edge or a specific color blob or corner.
Right.
The convolution operation slides this filter across the entire input image, step by step. At each position, it calculates a weighted sum of the pixels the filter is currently covering. The result is an activation map or feature map that shows where that specific feature was detected strongly in the image.
And you use many different filters.
Yes. You learn dozens or hundreds of different filters in parallel. One learns horizontal edges, another diagonal lines, another greenish patches, and so on. Crucially, the network learns the best filters to use for the task during training via backpropagation. It figures out what features are important.
Okay, so convolution finds local patterns. What about pooling? That usually comes after convolution.
Pooling layers are about reducing the spatial size of the representation. Downsampling.
Why do that?
Two main reasons. First, it makes the computation more manageable as you go deeper into the network. Second, it helps make the learned features more robust to small variations in location. If a feature is detected slightly shifted, pooling helps the network still recognize it.
Like zooming out slightly on a photo, details blur, but the main objects remain.
Exactly. The most common type is max pooling. It takes a small window, say 2 by 2 pixels, and just outputs the maximum value within that window, discarding the rest. It keeps the strongest activation for that feature in that local region.
What about average pooling?
Average pooling takes the average value in the window. It's smoother, less aggressive than max pooling. Max pooling is often preferred, especially earlier in the network, because it preserves the sharpest features, which can be important for object recognition. It helps achieve a degree of translation invariance.
Got it. Now, training these huge CNNs, like the famous ones VGG or ResNet, from scratch on millions of images, that takes massive compute power and data. Most people can't do that.
Absolutely not, which is why transfer learning is so incredibly important and practical. This is a must-know concept, especially if you're aiming to be effective quickly.
What's the core idea?
You take a powerful CNN model that someone else has already trained on a massive general data set, usually ImageNet, which has millions of diverse images across 1,000 categories.
Okay, a pre-trained model.
Right. This model has already learned to detect a rich hierarchy of general visual features, edges, textures, shapes, object parts in its lower and middle layers. Those learned features are often useful for many different vision tasks.
So you reuse that knowledge, like learning to drive a truck when you already know how to drive a car.
Perfect analogy. You take the pre-trained network, freeze the weights of the early convolutional layers, the feature extractors, and just replace or retrain the final classification layers to fit your specific new task.
Like classifying different types of flowers instead of the original 1,000 ImageNet classes.
Exactly. Or detecting specific defects in manufacturing or classifying medical images. You only need to train the last few layers on your smaller, specific data set. This saves enormous amounts of training time and data requirements. It's the standard way most people apply CNNs in practice.
Are there situations where transfer learning doesn't work well? What's the potential pitfall?
The main issue is domain mismatch. If the pre-trained model was trained on everyday photos, cats, dogs, cars, and your target task involves something visually very different, like, say, microscopic images or satellite imagery or abstract art.
The learned features might not be relevant.
Exactly. The low-level features like edges might still transfer, but the higher-level features learned on photos might not be helpful for understanding cells under a microscope. In those cases, you might need to fine-tune more layers of the pre-trained network, or even train from scratch if you have enough data in your target domain. Recognizing that mismatch is key.
This ability for machines to see using CNNs and transfer learning, it's revolutionized fields. The curriculum mentions autonomous vehicles, object detection, lane finding.
Huge impact there, yes. And medical imaging, too, analyzing x-rays, detecting tumors in scans. CNNs are everywhere. Visual data is important.
Okay, we've tackled the brain's architecture and given it sight. But what about tasks where order matters, where history and context are everything? That brings us to Unit 4, sequential data.
Right, things like text, speech, music, financial time series. The meaning depends fundamentally on the order of the elements. A standard feed-forward network, or even a CNN, treats each input independently. It has no inherent memory of what came before.
So just shuffling the words in a sentence would completely confuse it, even if the same words are present.
Precisely. We need an architecture with memory. Enter recurrent neural networks, RNNs.
What's the key difference in an RNN?
The defining feature is a feedback loop. The output of a neuron, or a layer, at one time step is fed back as input to itself at the next time step. This creates an internal state or memory that captures information about the previous elements in the sequence.
The analogy you used earlier, reading a book, understanding the current sentence depends on remembering the plot and characters from previous pages. The RNN's hidden state is like that running memory.
Exactly. That hidden state acts as a summary of the past sequence relevant to predicting the next step.
Sounds powerful. But standard, simple RNNs have a notorious problem, right? Especially with longer sequences.
Oh yeah. The big one is the vanishing gradient problem. It's kind of the flip side of the exploding gradient problem we sometimes see with high learning rates.
How does vanishing gradient affect RNNs?
Remember, backpropagation calculates gradients by working backwards through time in an RNN. Because of the chain rule, multiplying many small numbers together, the gradient signal from errors far back in the sequence can shrink exponentially as it propagates backwards.
So the influence of early inputs fades away.
It fades dramatically. By the time the gradient signal reaches the beginning of a long sequence, it might be practically zero. This means the network effectively can't learn long-range dependencies. It has very short-term memory. It forgets the beginning of the sentence by the time it gets to the end.
Which is obviously terrible for understanding language or long musical pieces. How did the field fix this fundamental memory limitation?
With more sophisticated recurrent units that have internal mechanisms, or gates, to control the flow of information and memory much more carefully. The most famous and influential is the long short-term memory, LSTM, cell.
LSTMs. These seem like a cornerstone of sequence modeling. The analogy used is a smart secretary.
I like that one. Think of a standard RNN neuron as just passing along whatever information it gets. An LSTM cell is much smarter. It has a separate cell state, which acts like a conveyor belt running through time, the long-term memory.
Okay, the memory tape.
And then it has these special gates, essentially small neural networks with sigmoid activations that learn to control what information gets written onto the tape, what gets read from the tape, and what gets forgotten.
Let's break down those gates. This feels like key mastery level detail. First gate.
The forget gate. It looks at the previous hidden state and the current input and decides what information from the old cell state is no longer needed and should be thrown away or forgotten. It's like the secretary shredding outdated memos.
Makes sense. Clear out the old. What's next?
The input gate. This decides what new information from the current input and previous hidden state is important enough to be stored in the cell state. It has two parts. One decides which values to update, and another creates a vector of candidate values to add, like deciding which new facts are worth filing away.
Okay, forgot old stuff, decided on new stuff. Then what?
Then you update the actual cell state. Forget the designated old parts, add the designated new parts. That cell state, the memory tape, then runs along to the next time step. Finally, there's the output gate.
What does that one do?
The output gate decides what parts of the updated cell state should be outputted as the hidden state for this time step, which influences the next steps, predictions, and gate decisions, and potentially as the final prediction for this step. It filters the memory to produce the relevant output right now, like the secretary summarizing the key points for the current meeting.
Wow, okay. So it's actively managing memory, forgetting, storing, retrieving. That's how it overcomes the vanishing gradient and remembers things for much longer.
Exactly. The cell state provides a clearer path for gradients to flow back through time, and the gates learn to protect important information over long durations. LSTMs and similar gated units like GRUs, gated recurrent units, were a massive breakthrough for sequences.
And this capability really unlocked progress in things like machine translation and chatbots, often using an encoder-decoder architecture, also called sequence-to-sequence models.
Yes, C2-sec models were a huge step, often built using LSTMs or GRUs initially. The idea is elegant, like a human translator.
How does it work?
You have two RNNs, or LSTMs. The encoder reads the entire input sequence, say an English sentence, step by step. It doesn't produce an output at each step. Instead, it compresses the meaning of the whole sentence into a single fixed-size vector, often called a context vector or thought vector. That's the final hidden state of the encoder.
Okay, so it summarizes the input, then the decoder.
The decoder is another RNN that takes that context vector as its initial state. Its job is to generate the output sequence, say the Spanish translation, one word at a time. At each step, it predicts the next word based on the context vector and the words it has generated so far.
Clever. Compressing meaning, then generating from that meaning.
It worked remarkably well. But even LSTMs have limitations with extremely long sequences, and processing sequences step by step is inherently slow. This led to the next major revolution.
Which everyone talks about now, transformers.
Transformers, yes. The architecture behind models like BERT, GPT-3, ChatGPT, all the big players today, they threw out the recurrent structure entirely.
No more step-by-step processing.
Nope. Transformers process all the words in the input sequence in parallel. The key innovation that allows this is the attention mechanism, specifically self-attention.
Attention. What does that let the model do?
Attention allows the model, when processing a particular word, to look at all other words in the sequence and dynamically calculate how relevant each of those other words is to understanding the current word in context.
Ah, so if it sees the word bank.
Exactly. The self-attention mechanism can look at the surrounding words. If it sees river nearby, it knows bank means the edge of the river. If it sees money or account, it knows it means a financial institution. It weighs the influence of other words dynamically.
And doing this in parallel makes it much faster and scalable than RNNs.
Massively faster to train. And it captures long-range dependencies even more effectively than LSTMs in many cases. This parallelization and the power of attention are what enabled the huge scale of modern large language models, LLMs. Understanding that leap RNNs to LSTMs to transformers is basically understanding the history of modern NLP.
And the applications are obvious. Better translation, text summarization, question answering, building incredibly sophisticated chatbots. It's transformed the field.
Okay, we've covered a ton of theory, the architectures, the learning mechanisms, but Unit 5 is where the rubber meets the road, taking these models from a Jupyter notebook into the real world. Professional practice.
Absolutely. You can have the most elegant model on paper, but if you can't build it reliably, evaluate it properly, debug it when it breaks, and actually deploy it, it's just an academic exercise. Bridging that lab-to-life gap is crucial.
The curriculum really stresses debugging and troubleshooting mastery. This sounds less glamorous, but maybe more important day to day, honestly. It's probably where experienced practitioners spend a lot of their time. Models fail in subtle ways in production. Data drifts, concepts change, weird edge cases pop up. Being able to diagnose why your amazing model suddenly started making bad predictions 6 months after deployment, that skill is worth its weight in gold. It's often harder than building the initial model.
Before we even get to debugging failures, we need to know if the model is succeeding in the first place. Evaluating performance. The curriculum points out that just using accuracy, the percentage of correct predictions, can be really misleading.
Oh, dangerously misleading, especially with imbalanced data sets. Imagine you're detecting a rare disease that only affects 1% of the population.
Okay.
A stupid model that just predicts no disease for everyone would be 99% accurate. But it's completely useless because it never finds the actual cases you care about.
Right. Accuracy looks great, but the model is worthless. So we need more nuanced metrics. Precision and recall, let's define those clearly.
Okay, precision answers the question. Of all the times the model predicted the positive class, your example predicted spam or disease, how many times was it actually correct?
So precision is about minimizing false positives, making sure when it says yes, it's likely right.
Exactly. High precision is critical when the cost of a false positive is high. Like in spam filtering, you really don't want important emails incorrectly flagged as spam. Or maybe in recommending products, you don't want to recommend totally irrelevant things.
Okay, that's precision. What about recall?
Recall answers a different question. Of all the actual positive cases that existed in the data, how many did the model successfully find?
So recall is about minimizing false negatives, making sure you don't miss the things you're looking for.
Precisely. High recall is paramount when the cost of a false negative is high. Think medical diagnosis. You absolutely cannot afford to miss detecting a disease, a false negative, or fraud detection missing a fraudulent transaction is costly, or identifying critical safety hazards. In these cases, you prioritize finding all the positives, even if it means you get a few more false alarms, lower precision.
So there's often a trade-off between precision and recall. Tuning your model might increase one but decrease the other.
Very often, yes. It depends on the classification thresholds you set. Understanding this trade-off and choosing the right metric or balance for your specific application is a hallmark of a professional. If you're guiding students, making them articulate why they chose precision over recall, or vice versa, for their project is key.
And if you need a single number, that balances both.
The F1 score. It's the harmonic mean of precision and recall. It gives a good combined measure, especially useful when you need a balance or when the class distribution is uneven. It penalizes models that are extremely good at one but terrible at the other.
Got it. Okay, evaluation mastered. Now, the tools, the ecosystem you work in. Managing a project from idea to deployment requires a whole arsenal. How do you categorize these tools?
We can think about them by use case and maybe difficulty or level of abstraction. For someone just starting, you want tools that are easy to use and get you results fast.
But beginners start.
Exactly. Top of the list here is Keras. It's a super high-level API, often described as training wheels for deep learning. It wraps lower-level frameworks like TensorFlow or PyTorch and makes defining and training models incredibly straightforward, great for rapid prototyping.
And where do you run Keras? You need compute power.
That's where Google Colab comes in. Think of it as a free supercomputer in your browser. It's a cloud-based Jupyter notebook environment that gives you free access to GPUs and TPUs, absolutely essential for learning and experimenting without needing expensive hardware.
And the environment itself, Jupyter Notebooks.
The standard interactive development environment for data science and ML. You mix code, text, equations, visualizations all in one document. Perfect for exploration and sharing results. Keras plus Colab plus Jupyter is a classic beginner stack.
Okay, fundamental, but maybe not strictly deep learning. Git and GitHub.
Non-negotiable professional skill. Git is your time machine for your code. It's version control, tracking changes, collaborating with others, rolling back mistakes. GitHub, or similar platforms like GitLab, Bitbucket, is where you host your Git repositories. You absolutely must learn Git. And for advanced users, thinking about versioning data and models with tools like DVC is also important, but Git is the bedrock.
Right. Now let's move up a level. The core frameworks that Keras often sits on top of. The big battle. TensorFlow versus PyTorch.
So the two giants, TensorFlow, TF, developed by Google, is maybe the more established in terms of production deployment. It has a very comprehensive ecosystem, TensorFlow Extended, TensorFlow Lite for mobile edge. Historically, TF focused on static computation graphs.
Meaning you define the whole network structure up front.
Yeah, you define the graph, then you execute it. This allows for optimizations and easier deployment, but debugging could be trickier, because the graph wasn't as flexible or easy to inspect mid-execution in older versions. Though TF 2.x embraced eager execution, making it more dynamic like PyTorch.
Okay, and its rival, PyTorch. From Facebook, now Meta.
PyTorch gained huge popularity, especially in the research community, because it felt more Pythonic. It uses dynamic computation graphs. The graph is built on the fly as the code executes.
What's the advantage, though?
Much easier debugging. You can use standard Python debuggers like PDB, print tensors, use loops and conditionals just like normal Python code. It feels more intuitive for many people coming from a Python background. It's generally seen as having a gentler learning curve for experimentation.
So which one should you learn?
Honestly, both are powerful, both are widely used. Many concepts transfer. PyTorch might be slightly easier to start with for research and prototyping. TensorFlow might have historically had an edge for robust, large-scale production deployment pipelines, though PyTorch is catching up fast there too, with TorchServe, etc. Knowing both is ideal, but starting with one and getting good at it is fine.
Okay. What about specialized tasks, particularly language?
If you're doing natural language processing, NLP, the first place you go is Hugging Face Transformers. It's not just a framework. It's a massive library and hub.
What do they offer?
Thousands of pre-trained transformer models, BERT, GPT-2, T5, etc. For almost any NLP task you can imagine, text classification, question answering, summarization, translation, plus tools for training, fine-tuning, and deploying them. It's an indispensable resource for NLP practitioners.
Right. Now, taking our trained model and actually showing it to someone or deploying it, we need tools for building interfaces and visualizing results.
Yeah, making your work accessible is key. For quickly building interactive web applications directly from your Python scripts, Streamlit is fantastic. It feels like magic. Sometimes you add a few lines of Streamlit code, and suddenly you have sliders, buttons, charts, and a shareable web app. Great for demos or internal tools.
And for even faster demos.
Radio is excellent for that. It's designed specifically to create simple web UIs for your ML models instantly. Input boxes for text, image upload fields, sliders hook it up to your model's predict function, and boom, you have a shareable demo link in minutes. Perfect for quick tests or sharing with collaborators. It's the instant demo booth.
Okay, demos covered. What about tracking the training process itself? Watching those loss curves, comparing experiments?
You absolutely need visualization and experiment tracking. The standard built-in tool for TensorFlow, and usable with PyTorch too, is TensorBoard. It's your training dashboard. Lets you log metrics like loss and accuracy over time, visualize the model graph, view histograms of weights, even display images or audio. Essential for debugging training runs.
And for more advanced tracking, especially in research or teams?
Tools like Weights and Biases, Wandvins, are very popular. They offer a more comprehensive platform. Think of it as a research lab notebook in the cloud. It tracks all your experiments, hyperparameters, code versions, system metrics, saves model checkpoints, facilitates collaboration, helps with hyperparameter sweeps. It's more fully featured than TensorBoard for managing complex research projects.
That's a comprehensive toolkit. Okay, let's tie a lot of this together. The curriculum uses Netflix as a case study. How does a company like that use deep learning in the wild?
Netflix is a prime example of combining multiple ML and DL techniques for massive business impact. Their recommendation engine is legendary.
It's not just one algorithm, right?
No way. It's a complex hybrid system. But they definitely use RNNs, or LSTMs, transformers now perhaps, to model the sequence of your viewing history. What did you watch before? How long did you watch it? What time of day? The order matters.
So sequence models for user behavior. What else?
They use CNNs extensively for analyzing the content itself, especially the visual aspects. Think about the thumbnails or posters they show you.
Ah, they optimize the pictures.
Absolutely. They use CNNs to understand the visual content of a movie or show and select or even generate the thumbnail image that is most likely to make you, specifically, click play. It's highly personalized visual recommendation. They also use traditional methods like collaborative filtering. Users who watched X also watched Y. It's a blend.
And the impact isn't trivial. The numbers are huge.
Staggering.
Yeah.
Reportedly, something like over 80% of the hours streamed on Netflix originate from their recommendation algorithms. And the estimated value, they claim it saves them over $1 billion per year just by reducing customer churn. If you always find something good to watch quickly, you're less likely to cancel your subscription.
That personalized thumbnail thing is the real wow detail for me. Same movie, different images for different users.
Exactly. A CNN analyzes the movie, identifies key scenes or characters. Your user profile suggests you like action. Boom, you see a thumbnail with an explosion. My profile suggests I like romance. For the exact same movie, I might see a thumbnail of the lead couple embracing. It's using deep learning vision capabilities to optimize the visual hook based on learned user preferences. That's sophisticated applied AI.
Okay, we've journeyed from the absolute basics through architectures, tools, and a major real-world application. The final stretch, looking ahead. How do we make sure the knowledge we've built today stays relevant? How do we achieve technology evolution resilience?
That's the beauty of focusing on the fundamentals. The core concepts, backpropagation, gradient descent, convolution recurrence, attention, these are mathematically grounded principles. They aren't going away.
So even if the specific frameworks change, maybe PyTorch 5 looks different or some new framework emerges.
If you understand how they work underneath, what a convolution is, what attention means, you can adapt much more easily. You're not just learning to use a tool, you're learning the underlying mechanics. That fundamental knowledge is resilient to the churn of specific libraries. And that resilience translates directly into exponential career value. AI expertise, genuine expertise built on fundamentals commands a significant premium. We're talking potentially 50, 100% higher compensation compared to non-AI specialized roles in tech.
Okay, so fundamentals are key for future-proofing. Looking towards, say, 2030, what are the big breakthroughs or trends that someone mastering AI today should be watching? Let's start with multimodal AI.
It feels inevitable. It's about breaking down the silos between different data types. Today, we often have separate models for vision, text, and audio. Multimodal AI aims to process and understand information from multiple sources simultaneously, just like humans do.
So an AI that can watch a video, listen to the soundtrack, and read the subtitles, integrating all of that to understand what's happening.
Exactly. Or understand a web page by looking at the layout, reading the text, and analyzing the images together. This is crucial for building truly intelligent assistants, more capable robots, and richer human-computer interaction. It requires fusing representations learned from different modalities.
Interesting. What about changes in the hardware itself? Neuromorphic computing sounds futuristic.
It is, but it's progressing. It's a fundamentally different approach to building computer chips. Instead of the standard von Neumann architecture where processing and memory are separate, neuromorphic chips try to mimic the structure and function of the human brain more directly.
Meaning lots of simple processors like neurons working in parallel.
Yes, often operating asynchronously, based on spikes, like biological neurons, rather than a central clock. The big potential advantage, ultra-low power consumption.
Ah, so AI that doesn't drain your phone battery in 5 minutes.
Potentially, yes. This could enable much more sophisticated AI to run continuously on edge devices, wearables, sensors, smartphones, cars, without needing constant connection to the cloud or massive batteries. This directly fuels the next trend, edge AI and distributed intelligence.
Moving AI off the cloud and onto the device itself.
Exactly. Processing data locally where it's generated. Two huge benefits. First, privacy. Sensitive data, like from your personal health sensors or home cameras, doesn't have to be sent to a central server. Second, latency. You get instant responses without waiting for a round trip to the cloud. Think real-time control in autonomous systems or instant feedback on your smartwatch. Neuromorphic computing could be a key enabler for powerful edge AI.
Makes sense. More power locally, better privacy, faster responses. But as AI becomes more powerful and more distributed, the ethical considerations become even more critical. The human element.
Absolutely paramount. As we develop these incredibly powerful tools, the responsibility on the creators and deployers grows immensely. We must lead ethically. The curriculum rightly emphasizes key challenges here.
Like fairness.
Yes. Ensuring our models don't perpetuate or amplify existing societal biases often hidden in the training data. This requires careful data auditing, bias detection techniques, and fairness-aware algorithms. It's an ongoing struggle.
And transparency, or explainability.
Crucial. We need to move beyond black box models, especially in high-stakes domains like healthcare or finance. Why did the AI deny the loan? Why did it recommend this treatment? We need methods like LIME or SHE to understand how the models arrive at their decisions.
And finally, accountability.
Maintaining human oversight. Knowing who is responsible when an AI system makes a mistake. Defining clear lines of accountability is critical, especially for autonomous systems. The human in the loop isn't going away. Their role is shifting to designer, reviewer, auditor, ethicist.
So the successful AI professional in 2030 isn't just a coder.
Not at all. There'll be someone who combines deep technical understanding with human skills, creativity, critical thinking, communication, empathy, and strong ethical reasoning. It's about augmenting human intelligence, not just replacing it. That synergy is the future. #Chag outro. So we've really covered the ground today. From those core ideas like bias and variance using analogies like dartboards and rolling balls, we moved through the building blocks, ANNs, activation functions, backpropagation, then into the specialized tools for seeing, CNNs, and for understanding sequences, RNNs, LSTMs, and transformers. We equipped you with the practical toolkit Keras, PyTorch, TensorFlow, evaluation metrics like precision and recall, and saw it all come together in the Netflix example. Finally, we looked ahead to multimodal AI, neuromorphic computing, and the vital human element. It's been a deep dive for sure.
It really has. Hopefully this serves as that solid guidebook for anyone on this journey, whether you're aiming for mastery or guiding others as a TA. If there's one piece of final advice synthesized from pretty much everyone who works in this field, what would it be?
Start building. Seriously, don't get stuck just reading theory.
Right.
Take a project, even a small one. Try to build something. Your first models will be terrible. That's okay. Embrace failure as data. Debugging a broken model teaches you more than reading another chapter. Stay curious. Keep experimenting.
Couldn't agree more. Build stuff, break stuff, learn stuff.
And maybe a final provocative thought to leave everyone with. The future isn't about fearing AI, nor is it about blindly worshiping it. It belongs to those who understand how to collaborate with it effectively, responsibly, ethically. The time to start building that understanding, that capability, is right now. The knowledge compounds and the curve is steep. Start today.